Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about the legacy of my colleague, Stephen Hawking. You know, after Stephen Hawking passed away, there were a number of interviews talking about his personal life, about his struggle with ALS, about his struggle to do physics. However, very rarely did an interview talk about his science. Well, that's what we're going to talk about today. Not just the legacy of the man, but the legacy of his work on black holes and the creation of the universe itself. Well, we have with us today a special guest. Once again, we have with us Dr. Ken Croswell, an astronomer at Berkeley, author of a number of great books, including Alchemy of the Heavens. I especially like his book, The Universe at Midnight. He's also the author of Magnificent Mars, Magnificent Universe, and we're going to talk to him about Stephen Hawking's astronomical contributions to science today. And we're going to talk today about black holes and the creation of the universe. Two areas where Stephen Hawking made an indelible mark in the scientific literature. First of all, we should say that not since Einstein have we had a figure, a towering figure, that made fundamental contributions to physics, but also engaged the public. And some people wonder, well, why is that? Why did a theoretical physicist capture the public's imagination? Well, in my personal opinion, I think that both Einstein and Stephen Hawking were, in some sense, messengers from the stars. You know, we dream about stars. Stars are in our dreams. Every night when we look in the night sky, we're overwhelmed by the splendor and the majesty of the starry heavens, and we begin to wonder, what does it all mean? Where did it come from? Where is it going? How do we make sense of this? Well, here was Einstein, here was Stephen Hawking saying, take my hand and I'll give you a guided tour through the universe. And so once again with us today, Dr. Ken Croswell, talking about the scientific legacy of my colleague, Stephen Hawking. So Ken, first question for you is, how did we first know about black holes? I understand that as soon as Einstein came out with relativity, already people were zeroing in on black holes. So explain to us a little about the prehistory of black holes.
Sure thing. Black holes, as you say, are predicted by Einstein's general theory of relativity, but it took us astronomers quite a while to actually find them in space. Now, I should define what a black hole is, of course, just so everyone's on the same page here. A black hole is an object in space that has such intense gravity that nothing can escape from it, not even light, the fastest thing in the universe. And black holes form when massive stars die and explode and then implode. The outer layers of the star go off into space at very high speed, and then the inner part of the star collapses into a black hole with such enormous surface gravity that nothing can escape it. And the very first black hole that we astronomers discovered in the constellation Cygnus, and it's called Cygnus X1 because it's the first X-ray source discovered in Cygnus. That means this object emits X-rays. So that tips us off that there was something unusual about this object in Cygnus because normal stars don't emit a whole lot of X-rays. This object was. And upon further investigation, we discovered that this object consisted of a bright blue star, massive star, much more massive than the sun, going around something dark, something that nobody could see. And through additional observations, we discovered that that dark object had so much mass that it must be a black hole. Now, it took a long time for us to absolutely be certain of this. And since you've mentioned Stephen Hawking, I should tell you that Stephen Hawking actually bet another physicist by the name of Kip Thorne that Cygnus X1 did not contain a black hole. And Stephen Hawking actually ended up losing that bet because now it's almost definite that Cygnus X1 contains a black hole. We think an object is a black hole if it's not emitting any light and it's got a mass greater than 3 times that of the sun. And the latest observations of Cygnus X1 indicate that it's 15 times the mass of the sun. So there's really no doubt anymore that Cygnus X1 is a system that contains a black hole. And in the 1990s, Stephen Hawking paid his bet to Kip Thorne The agreement was that he would give Kip Thorne a subscription to that well-known scientific journal, Penthouse.
Okay. And I remember back in the 1960s, there was all this controversy about quasars, quasi-stellar objects. They seem to be gigantic stars that seem to light up the heavens, but other people said, no. They're very distant and very powerful. So what is a quasar, and what is our present-day understanding of quasars?
Quasars are indeed very, very distant, and they are powered by black holes. Now, the type of black hole I just mentioned, Cygnus X1, is what's called a stellar mass black hole. It has only about 15 times the mass of the sun. But we now know that most of the giant galaxies of the universe, including our Milky Way, have at their centers supermassive black holes that may be millions or even billions of times the mass of the sun. And it's these big black holes, these supermassive black holes, that power quasars, because you have material falling into the black hole, the supermassive black hole at a galaxy center. Some of that material goes in, but before it goes in, it gets heated to enormous temperatures, very high temperatures, and anything that's very hot is going to radiate enormous quantities of light. And as a result, quasars are the brightest objects in the universe because of these big black holes. It sounds like a contradiction, actually, that something that emits no light, namely a big black hole, actually powers the brightest objects in the universe, these quasars. But that's the current thinking about quasars. You're absolutely right. In the 1960s, they were much more controversial. There were some people claiming, oh, no, they can't be that powerful. That just goes way beyond known physics. Well, if you've got a supermassive black hole on your side, you can do quite a lot of impressive things.
Okay, now, black holes are so bizarre, so crazy, that I understand that back in 1916, when the first black hole solution was found in Einstein's equations, Einstein himself could not get his head around black holes, right?
Well, that's my understanding, too. That, in fact, a number of people really didn't like the idea that nature could create these objects that were essentially cut off from the rest of the universe. Because, think about it. You could go right now to the planet Mars if you had a good enough rocket ship, and you could report back what you find on the planet Mars. Or you could go to Alpha Centauri, or you could go to some other star and tell us what you find. But if you go into a black hole and try to tell us what you find, well, you're not going to succeed, because your radio signals, which travel at the speed of light, will not make it out of the black hole. And that's, of course, even assuming you survive the trip. It's unlikely you would survive a trip into a black hole. But the point is, black holes are really not in contact with the rest of the universe. And that really offended the sensibilities of some scientists.
So, Ken, let's say you go outside, and you mentioned that there are galactic black holes at the center of the Milky Way galaxy. Well, first of all, if you were to go outside and look at the night sky, in which direction would you look if you want to see the center of the Milky Way galaxy, where by rights there should be a fireball?
Well, you would look at the constellation Sagittarius, which is visible best in the summer sky, in the southern part of the summer sky. The constellation Sagittarius is a constellation I talk about in my book, See the Stars. It looks like a teapot. It consists of 8 stars, and near the spout of that teapot is Sagittarius A star, which is the supermassive black hole at the center of our galaxy. This is the object about which everything else in our galaxy goes around. So the sun right now is traveling at very high speed around the galaxy, and it's going around this supermassive black hole, and so are all the other stars that you see with the naked eye at night. This supermassive black hole is 4 million times as massive as the sun and lies 27,000 light years from Earth. So we are in no danger whatsoever of falling into the black hole. However, there are lots of stars located within just 1 light year of the black hole, and some of them are in danger of falling eventually into the black hole. And surely in the past, our black hole, the big black hole at the center of our Milky Way, has swallowed other stars. But the short answer to your question is, if you want to see the direction in which this black hole lies, you can just look for the constellation Sagittarius.
Now, we've all seen pictures of galaxies like Andromeda, for example, the nearest galaxy. They sort of look like flying saucers with a bulge in the middle. However, when you look in the direction of Sagittarius, what do you see? Nothing. Blackness. Why don't we see this fireball at the center of the Milky Way galaxy where lurks a gigantic, monstrous black hole? Why can't we see this gigantic fireball lighting up the night sky like the moon?
Well, the supermassive black hole, Sagittarius A star, is fairly quiet right now. Nothing much has been falling into it, and so it's not really doing much at the moment. I have no doubt that in times past it was much more brilliant. Now, what we ought to be able to see in principle are all those stars around the black hole, because there are probably millions of stars. In fact, there are millions of stars located very close to that black hole. Unfortunately, we cannot easily see them because of all the dust in our galaxy. There's a lot of dust in our galaxy, and that dust blocks the light of those stars. So the black hole itself, we wouldn't be able to see even without the dust, but the stars, they have their light absorbed by the dust. So astronomers tend to observe them at infrared wavelengths, which penetrate the dust in our galaxy.
Okay, well, these things are so fantastic. Black holes are so incredible that Einstein couldn't get his head around it, and he even wrote a paper proving they couldn't exist. He showed that, according to current theory, if I have a swirling mass of gas where stars come from, is not sufficient to squeeze the gas to the point where it becomes a black hole. However, later, people like Robert Oppenheimer, who created the atomic bomb, found a new way to create a black hole implosion. So explain to us the difference between Einstein's original idea, which was incorrect, that a swirling bunch of gas is not sufficient to create a black hole, with the modern-day understanding, pioneered by Oppenheimer, who created the atomic bomb, of an implosion mechanism which Einstein never considered. Could you elaborate?
Yes, the modern view is that when a massive star dies, the outer layers explode. I mean, they shoot off into space, but the inner part of the star collapses and, as you say, implodes and gets compressed to enormous density. In fact, if you take Einstein's equations literally, the object actually becomes infinitely dense. And so that's how we think that actual black holes in space arise, when a massive star dies and its center collapses and gets compressed into a super dense object whose surface gravity is so enormous that nothing, not even light, can escape from it.
And then the question is, well, if it takes an implosion mechanism to create a black hole, what about our sun? Our sun is not going to explode like these giant stars. So does this mean, therefore, that our sun is not going to become a black hole?
Exactly. Our sun is safe from becoming a black hole. It will instead someday die by becoming a white dwarf, which is also a dense sort of star, but not nearly as dense as a black hole. If you were on the surface of a white dwarf star, you could easily escape from it.
Okay, now let me ask you the question that every child asks when they visit the planetarium, and that is, what happens if you were to gradually approach and then fall into a black hole? Heaven forbid. What's going to happen? Is your body going to be ripped apart? What happens if you slowly approach a black hole and begin to perhaps fall in?
Well, you will get stretched out by the tidal forces. For example, if your feet are facing the black hole and your head is facing away from the black hole, the gravity black hole will tug much harder on your feet than on your head. And if you get too close to that black hole, it will unfortunately spaghettify you. In other words, turn you into a long string of spaghetti. So I advise anyone listening not to get too close to a black hole.
Okay, now also as you get closer and closer to the black hole, you find a sphere called the event horizon. We think the sphere is going to be basically black, but can you explain how big is this thing? What is a event horizon, and why is the event horizon so much studied?
Well, the event horizon is the point of no return. You pass through the event horizon, and unfortunately you're not coming back to the rest of us to tell us what you have found. So you definitely want to stay outside the event horizon. Once you pass through that, you're not coming back.
Okay. In fact, there's a movie, Interstellar, And Kip Thorne, who recently won the Nobel Prize for gravity waves, was one of the consultants. And that movie was interesting because it had no Hollywood special effects. The so-called special effects as you approach the black hole were done by computers. A computer simulation of what happens if you get closer and closer to the black hole. However, I think Kip Thorne took a few liberties because he then went into what happens if you fall through the event horizon. So isn't it true that we physicists are a little bit fuzzy about what happens if you actually pass through the point of no return?
Well, certainly. I mean, these are things that no one has ever done, and who knows what actually happens. Often our theories prove to be in need of revision when we, for example, send a spacecraft to another planet. So, yes, in order to know for sure, there's probably only one way to do it, and that is you have to visit a black hole yourself. But again, I'm not sure it's something I would personally want to do.
And also, don't you get vast distortions of time as well as you get closer and closer to the event horizon, and someone's photographing you from a distance, looking at you, time slows down, right? And so as you approach the event horizon, you look like you're frozen in time. Explain that.
Yes, in fact, there's even a book that came out in the 1980s about black holes, and it's entitled Frozen Star, because from afar, what you say is absolutely right. An observer watching someone fall into a black hole would actually see that person who's falling in never actually reach the surface of or the event horizon. They would, because time is proceeding so much more slowly for the person outside the black hole, well outside the black hole, than for the person falling in. And, of course, these are all effects of relativity.
Okay, now, people say that in order to clinch it, we have to photograph the event horizon. That seems impossible. However, recently, scientists have lashed together several radio telescopes and zeroed in on the black hole at the center of our own galaxy, our own backyard. And they claim that one day we'll be able to have a close-up snapshot of the black hole. This is amazing.
Yes, it's very nice in radio astronomy. Radio astronomers are able to link up separate radio telescopes into what's called an interferometer, which allows a much sharper resolution than any individual radio telescope does. And in fact, a few years ago, radio astronomers used such an array to measure the distance to the very first black hole ever found, Cygnus X1. And it turns out that that black hole is a bit more than 6,000 light years away. And we know that because of the precision of the radio observation. And in like fashion, a radio interferometer can also resolve very, very superbly the black hole at the center of the Milky Way, the Sagittarius A star, which is located 27,000 light years from Earth. And so in that way, we can hope that we'll be able to detect the event horizon. And, of course, there are lots of stars around that black hole, so they presumably will provide the light and enough contrast with the event horizon. And, by the way, there's another supermassive black hole that might also get its image taken. It's in a giant elliptical galaxy called M87, and that galaxy is located 54 million light years from Earth. And you may say, whoa, that's 2,000 times farther than our supermassive black hole. Well, yes, it is, but that black hole happens to be about 2,000 times bigger, 2,000 times more massive than the black hole at the center of the Milky Way. So if we can actually successfully image the black hole at the center of our galaxy, we might want to then turn our attention to this big black hole at the center of the galaxy, M87, because they should be about equally difficult to observe.
Now, the resolution power of a radio telescope is related to its size. The bigger the radio telescope, the more radio waves it picks up, the better the resolution of the picture. But by lashing these radio telescopes together at distant points on the Earth, they tell me that you get an effective radio telescope the size of the planet Earth. And you can't get much bigger than that, right? So isn't that amazing that it's possible by lashing these telescopes together that we can create an effective telescope the size of the planet Earth itself? Isn't that amazing?
It is, yes. And as I say, that's how we measure the distance to Cygnus X1, the first black hole, even though it's very far away, much farther away than we normally measure distances to stars. So, yes, radio astronomers are very lucky that they're able to do that. And the reason they're able to do that is because radio waves are fairly long. They're not nearly as microscopic as light waves. So radio astronomers have that luxury to lash their telescopes together and create interferometers.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Dr. Ken Croswell, astronomer from Berkeley, author of a delightful book, The Alchemy of the Heavens. We're talking about the scientific legacy of my colleague, Stephen Hawking. And we talked about gigantic radio telescopes that can, for the first time now, begin to have a snapshot of the event horizon of the black hole lurking at the center of the Milky Way galaxy. This is incredible. And then the next question is, well, what does it look like? Well, it's probably going to be a sphere, but it's probably going to be black. And so I think some people may be a little bit disappointed that it's not explosive, that it looks basically like a black sphere. But, well, what are your thoughts about what we're going to find?
Well, I think that's right. We're not going to see anything explosive. This is a very quiet black hole. It's been a little bit of a mystery to astronomers why it is so quiet, given that there are so many stars around that black hole and so close to the black hole. And, of course, they're losing gas, and you would think the big black hole, Sagittarius A star, would be taking in some of that gas, and that heats things up, and it would be a little more active than it is. But nonetheless, in times past, I'm sure it was a lot more active. But in terms of what we are actually going to see with this imaging, I think your description is correct. We will see something that maybe won't impress that many people, but you have to realize what we're seeing here. This is the biggest black hole in the Milky Way galaxy. That's quite an impressive image when we can get it.
Now, what Stephen Hawking showed was that perhaps black holes are not totally black. Perhaps they gently seep out radiation called Hawking radiation because you have quantum mechanics. That is, you have the uncertainty principle involved, and so you get a certain amount of leakage from a black hole. But Hawking radiation, isn't it very faint? Isn't it very difficult to pick up? And some people suspect maybe that's why he didn't win the Nobel Prize. But tell us a little bit about Hawking radiation. It's pretty faint, right?
Yes, extremely faint, and in real black holes that we know of, it's probably undetectable. And so the thought was, well, maybe you could detect Hawking radiation from very small black holes. If, for example, at the beginning of the universe, small regions of the universe collapsed to form black holes that only have maybe the mass of an asteroid, because the Hawking's theory predicts that this Hawking radiation should be much more profuse with a smaller black hole. And so the hope was back in the 70s that maybe these mini black holes formed and we could detect gamma rays as they evaporate, because as these very small black holes lose mass by Hawking radiation, eventually they will completely run out of gas and completely vanish and emit gamma radiation. But unfortunately, that Hawking radiation has never been seen. So I think a lot of people probably think that these mini black holes don't exist. And as far as the big black holes, things like Cygnus X1 and Sagittarius A star, they are surely taking in far more mass than they are losing by Hawking radiation. So they are growing bigger with time rather than smaller.
And every physicist I know believes in Hawking radiation, because if we didn't find Hawking radiation, then quantum mechanics cannot be applied to black holes, and most of modern physics would collapse, which is horrendous. So in some sense, Hawking radiation has to exist, because if it didn't exist, we wouldn't be able to apply quantum mechanics to black holes. But because it's so faint, perhaps that's the reason why he never won the Nobel Prize. Well, here's another question for you. We talked about small black holes, and there's also the possibility that you can have wandering black holes that sneak up on you, and NASA actually tracks some of them. So after the break, I'll ask you a few questions about, is it possible that a black hole can sneak up on you, and you'd never know? Welcome back to Science Fantastic with Professor Michio Kaku. With us today is astronomer Ken Croswell, and we're talking today about the legacy of Stephen Hawking. Not his personal legacy, his personal triumph over ALS disease, but his scientific contributions to physics. And we talked about black holes and the fact that some black holes are actually wandering. As you look in the night sky, you see the distortion of starlight as some invisible object moves in front of the star, warping the light behind it. And that's how, even though you can't see the black hole itself, you can see the outlines of the black hole as it moves across the night sky. So the question is, what happens if one day we are caught flat-footed, caught off guard, if there's a wandering black hole next to us? So tell us, this black hole, if it's wandering, has the mass of a giant star. It could literally start to make the planets in our solar system wobble and perhaps even fling them into outer space, right?
It would be very bad news, but before I describe what's about to happen, understand this is extremely unlikely to occur because black holes are actually quite rare. Ordinary stars are much more common, and we don't see ordinary stars intruding into the solar system. The stars are very widely separated in our part of the galaxy. But let's imagine, hypothetically, there's a black hole that's heading our way. That's got, let's say, 15 solar masses, similar to Cygnus X1, the very first black hole ever found. What would happen? Well, at first, I presume this black hole would start disturbing the comets in the Oort cloud, far beyond the orbit of the planet Neptune and Pluto, and would start stirring up those comets and start sending some of those comets our way. So we would start suffering catastrophic impacts from comets. And then, as you say, as the black hole approaches closer, it would start disturbing the orbits of the planets themselves and could easily fling some of the planets out into interstellar space. And, of course, we could be one of the planets flung out into the cold. Or, what might be even worse, we could be flung into the sun. Or, at the very least, probably the Earth's orbit would no longer be as circular as it is now and would become much more elliptical, in which case the seasons on Earth would be much more extreme and much more unpleasant. It would go from being very cold to very hot as the Earth went around the sun. So a lot of very bad things would occur if a big black hole were to enter our solar system. But again, it is very, very unlikely that this is ever going to happen because even ordinary stars don't enter the solar system, and they are much more common than black holes are. The difference, of course, is, as you point out, with a black hole, we can't really see it coming, whereas with a star, even a faint star, we can see it coming.
Right. And as you correctly point out, a collision with one of these things is extremely rare, but we track them. In fact, several are being tracked even as we speak. And yeah, they're not connected to any one particular location in the galaxy. Some of them are not even in the galactic plane. But yeah, it's something that we should think about, but not lose any sleep over. Well, now let's move on to the Big Bang, because Stephen Hawking also made contributions there, even though, of course, it's still mysterious as to the energy source of the Big Bang. But tell us a little bit about inflation. Inflation has pretty much changed the landscape, right? Forced us to contemplate perhaps multiple Big Bangs. Tell us a little about what is inflation and why has it changed our attitude towards the Big Bang?
Well, the Big Bang is the great explosion that occurred 13.8 billion years ago and that gave birth to our universe. And we now realize that just a split second after the Big Bang, the universe inflated enormously. And this so-called inflation solves a number of cosmological problems. For example, it solves the flatness problem. Our universe is, as far as we can tell, perfectly flat, by which I mean that geometry in the universe is Euclidean. It's not curved one way or the other. And inflation solves that problem by puffing up the universe so enormously that even if the universe had some initial curvature, it becomes essentially flat after inflation. So that's one problem that inflation solves. Another problem that inflation solves is called the horizon problem, which is, why is it that when we look in one direction in the universe and then we look in exactly the opposite direction in the universe, they have the same temperature? I mean, if you think about it, they're separated by over 20 billion light years. They can't have been in contact unless you had inflation. Inflation would have puffed up regions that were originally in contact to enormous dimensions. So even though those two different parts of the universe are right now separated by 20 billion light years, prior to inflation, they were in contact and could share information in a sense and have the similar properties. So that today, even though we see them very far apart and we see that they have similar properties, there's a reason they have those similar properties. That's because prior to inflation, they were close together. And then after inflation, they were hurled very, very far apart.
Now, inflation was proposed by my colleague Alan Guth of MIT, who may eventually win the Nobel Prize for the inflation theory. So I asked him on radio, if the Big Bang was a quantum event, isn't there a certain probability that it could happen again and again and again? And he said, yeah. It means that there could be multiple universes out there, that even as we speak, Big Bangs could be happening all the time. So doesn't that change our viewpoint of the universe? That our universe could be incredibly bigger than we originally thought, and there could be whole regions of the universe where Big Bangs are taking place even as we speak. This is mind-boggling stuff, right?
Yes, well, as long as you have the laws of physics, which permit quantum fluctuation. Normally, quantum fluctuations are very small, but if you wait a long enough time, you could conceivably give birth to another Big Bang and a whole other universe.
Well, unfortunately, our time is up. Once again, you've been listening to Science Fantastic with Professor Michio Kaku. Our special guest today was Dr. Ken Croswell, astronomer of Berkeley, author of Alchemy of the Heavens. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Let's move on to the first listener phone call.
My name is Levi Schumacher. I am not listening to the radio. I saw your post on Twitter, Dr. Michio Kaku, and I love all your work. I'm a geophysicist from Colorado School of Mines, and my question is, how far are we away from anti-gravity propulsion for use in aircraft in the private sector? And what method of physics would we use? Would it be electrostatic, nuclear, or what fuel sources and or physics and chemistry and mechanical engineering? Thank you.
Okay, well, thanks for the question. I hate to disappoint people out there. We've all seen movies like Back to the Future, where we have hoverboards, skateboards that literally glide right over the surface of the Earth because of anti-gravity. We've seen anti-gravity, for example, in Star Trek. We've seen Captain Kirk, for example, go outside the Enterprise, controlling where he is using anti-gravity. But sorry about that. It turns out that anti-gravity, the kind of thing you see in the movies, does not exist. Now, let me explain why. And what about substitutes for anti-gravity? Well, first of all, we have something called antimatter, which is the opposite of matter. Electrons have negative charge. We all learned that in high school. But positive electrons are positrons, and they have the opposite charge. They're positively charged. So antimatter has an opposite charge. But you see, light has no charge, and anti-light is light. So the antiphoton, a particle of light, is the photon itself. It is its own antiparticle. Now, gravity is broken up into gravitons, And if you do the same calculation, you find that anti-gravitons is gravitons. Sorry about that. So in other words, as far as the Earth is concerned, we do not have a source of anti-gravity, especially like the hoverboards in the movie Back to the Future. Now, there is anti-gravity on the cosmological scale. That's called negative energy, and that's blowing the universe apart. The energy of the Big Bang, that is pushing the gravities apart, pushing the galaxies apart, that is called negative energy, dark energy, and it is anti-gravitational. But it is extremely weak. It only exists on galactic scales. And so if you want to have a hoverboard, sorry about that, it's not going to work. So people have tried other methods to create anti-gravity. One way of creating artificial gravity on a space station is to spin it, and that gives you centrifugal force, which allows you to create an artificial gravity even in the weightlessness of outer space if you spin the spacecraft. However, that's expensive, and NASA has no plans at the present time to spin its spacecraft. Too expensive. Then you have magnetism, which I think is the most logical choice. For example, if we have room temperature superconductors, then the dream of hoverboards could become a reality. Now, what's the catch? The catch is that room temperature superconductors have not yet been found. We have superconductors at medium-low temperatures, but not at room temperatures. And that's the problem. If one day some inventor can create room temperature superconductors, then yes, you could hover right over a skating rink over the air rather than touching the ice. And so my advice to people who believe in anti-gravity is, well, you may have to wait a while. Sorry about that. Okay, let's move on now to the next listener phone call.
Hello, this is Garrett. I'm calling from Seattle, Washington. And the question that I wanted to ask is, based on the current theories for space-based propulsion technologies that are out there, which ones do you think are the most viable options for us to be able to reach Mars and the asteroid belt? Thank you very much.
Well, you ask a question that is at the center of politics right now because, well, the President of the United States has made it official. First, we go to the moon, then to Mars, and then beyond. So then the question is, what is the best economical and fastest way to go to these celestial bodies? Well, first of all, to the moon, that's a piece of cake. A chemical rocket can get there in 3 days. You leave on Monday. You arrive on Thursday and come back over the weekend. You can have a weekend jaunt on the moon. And also, I think that our grandkids may have the option of honeymooning on the moon because it's really a hop, skip, and a jump from the Earth. And prices have been dropping dramatically, and so it may not cost that much to honeymoon on the moon. Now, Mars is a little bit different. Mars is farther away. A chemical rocket, like the Saturn V, would take about, 7 to 9 months to get to Mars on a one-way trip. A round trip would therefore be about 2 years. Now, is it possible to reduce the speed? And the answer is yes. Elon Musk says he can probably get it down to a few months, not 7 to 9 months, but how? He didn't say how. Well, it turns out that there is an engine called the plasma ion engine, which shoots out a hot ionized plasma from the exhaust and allows you to go to Mars literally in a few months. So a round trip may just take half a year. And so what's the catch? There's always a catch someplace, right? It turns out that plasma ion engines depend upon their energy source. If that energy source is nuclear, then yes, it may be possible, at least on paper, to create a plasma ion engine that will reach Mars in just a few months. The catch is, of course, that it is nuclear, and we have to be very careful that it doesn't blow up on the launch pad or contaminate the astronauts or cause a meltdown on Mars. So there's all these problems that have to be solved. One way of doing it is to fire up the engines chemically and assemble the rocket in outer space, just like we assemble the space station in outer space, and then fire up the engine, then fire up the nuclear reactor. Well, that's still pretty risky. I personally hope that we don't have to go that route, but it is a route that is being talked about, and that is the nuclear plasma ion engine. Now, what about warp drive? Well, that's a whole nother question, because on Star Trek, they make it seem so easy. You just turn on the antimatter impulse engines and go to warp factor, whatever, and there you are. However, not so fast. It turns out that warp drive may be possible, but it requires a technology far more advanced than anything we can muster here on the planet Earth. And so just to summarize, to go to Mars in a chemical rocket takes about 7 to 9 months, 2 years for a round-trip mission. But a question mark, can a plasma engine cut down the cost and time involved? And that is still a question mark. Okay, well, let's move on now to the next listener phone call.
Hey, so my name is Caleb Woods, and I'm from Jasper, Alabama. First off, I just want to say I'm a huge fan, and thank you for being such a great communicator of science. I have what is really a two-part question. First, how successful do you think the dark matter detectors being built on Earth will be in the next decade? And second, what type of space telescope or other technologies should we be trying to build for the purpose of off-planet detection of dark matter?
Well, you asked a question about dark matter, and dark matter is extremely difficult to detect precisely because it is dark. It is invisible. Now, you may say to yourself, what? If something is invisible, then how do we know that it even exists? Well, that was the problem for many decades. You see, back in the 1960s, astronomer Vera Rubin conjectured that dark matter must exist. Because, you see, the galaxy is spinning too fast. Like a pinwheel. By rights, it should fall apart. But here we are, safely in the Milky Way galaxy. It's been stable for 10 billion years. And what holds the galaxy together? By rights, the galaxy is moving 10 times too fast. By rights, it should fly apart like a pinwheel that is out of control. But here we are in a very stable galaxy. Well, the postulation was that there's a halo of dark matter surrounding the Milky Way galaxy. But what is it made of? Well, we looked at the usual candidates, maybe neutrons, maybe neutrinos, things that have neutral charge. Nope. One by one, we cross them all off. In other words, dark matter really is a new form of matter. So every high school textbook is wrong when it says that the universe is mainly made out of atoms. Nope, sorry about that. Dark matter is 10 times more plentiful than ordinary matter. So how do we detect it? Well, there's several proposals that have been made. One of course, is to look at the bending of starlight in outer space, and we have maps of dark matter as a consequence. But we want to capture it in the laboratory. We want to touch it. We want to play with it. And we don't simply want to have maps of it that are light years away. There are two ways to do it. The first is to build an atom smasher, the Large Hadron Collider, which can create dark matter. And that's what we're doing now. The Large Hadron Collider found the Higgs boson, and we're now trying to create dark matter in the laboratory. It's not dangerous, don't worry, because dark matter is practically inert when it interacts with ordinary matter. The second is to create a detector on the Earth, as the questioner asked. Let's say I have a swimming pool of cleaning fluid. In that swimming pool of cleaning fluid, there's lots of hydrogen with a proton. If dark matter hits the proton, it'll shatter the proton, and we should be able to detect the image of the shattering process. A piece of light, a little bit of light should be emitted when the proton is smashed apart. So we are living in a wind of dark matter. There you are, sitting in your living room, thinking that there's only atoms in the room, but no. We are living in a wind of dark matter, and this wind of dark matter may eventually collide with a proton, and in that way, we might be able to detect it. So, the leading detectors around the planet Earth are looking for it. Somebody could win the Nobel Prize any day by announcing that they've detected the spark of a dark matter collision in their detector, or that one day the Large Hadron Collider will detect dark matter. Now, why am I interested in this? I'm interested in this because I work on string theory. We think string theory is the theory that eluded Einstein for the last 30 years of his life. And string theory predicts a new form of matter, a new octave of the string. We are the lowest vibratory mode of the string. Everything you see around you is a vibrating string, and they're stable. But there's another layer above it, the next octave, and that layer, bingo, has a layer which is invisible and acts just like dark matter. So the candidate for dark matter is called the photino. We have not yet found it, but the hope is that we will find the photino either by creating it or by looking for its implosion with a proton in a detector, and perhaps that could pave the way for a Nobel Prize. But until then, we can only hope. Okay, let's move on now to the next listener phone call.
Hi, I'm Brendan Glover from Indiana, Pennsylvania. My question is, does consciousness require continuous time? If so, can artificial intelligence experience consciousness?
Wow, you asked the $64,000 question that everyone is debating. Right now, artificially intelligent machines are not conscious. But what happens when they do become conscious? What does that mean? What does that mean for our safety, for the economy, and so on and so forth? Well, first of all, let me say that all technologies are double-edged swords. One side of the sword can cut against disease, poverty, ignorance, and usher in an age of Aquarius. The other side of the sword can cut against people, cut against you and me. And what is the difference between these two? Who controls? Who wields the sword? Who controls the double-edged sword of technology? The same thing with artificial intelligence. Right now, artificial intelligence is still pretty primitive. Our most advanced robots have the intelligence of a cockroach. In fact, if you take a cockroach and put a cockroach in the forest, immediately the cockroach will know what to do. It'll go out and find food. It'll find mates. It'll find shelter. You don't have to program the cockroach. The cockroach all by itself can figure it all out. Now, you take our most advanced computer, our most advanced robot, and you put it in the middle of a forest. What does it do? It gets lost. That's how primitive our robots are. And, however, let's be fair, even though it means that for decades to come, robots are not going to be a threat, eventually they're going to be as smart as a mouse, then a rat, then a rabbit, then a cat, then a dog, and finally they'll be as smart as a monkey. At that point, they could become conscious, and they could be dangerous, in fact. What is the tipping point? The tipping point is self-awareness. Robots are adding machines. We forget that. They don't know who they are. They don't know the difference between a human or a robot. But eventually, they'll figure it out. I mean, after all, we are made out of wetware. We figured it out. So hardware, why can't hardware do what wetware already does? Well, that's a big question, of course. But self-awareness, robots don't have it yet. Maybe by the end of the century they'll have self-awareness. At that point, they could be dangerous. At that point, I think we should put a chip in their brain to shut them off if they have murderous thoughts. But in the meantime, I think robots can energize the economy, provide jobs, open up whole new areas of economic activity. So the short term is, I think robots are going to be one of the drivers of economic growth. In the long term, however, we have to make sure that we control this technology because it could easily slip out of our control. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Corey, and I live in Boulder, Colorado. I'm curious, knowing that ice ages and civilizations historically In our infantile attempt to become a Type 1 civilization, are elevated CO2 levels beneficial in trying to ward off an incoming ice age? Thank you for your consideration. I greatly enjoy following you over the last several years, if not the last decade. Thank you for all you do. Bye-bye.
Well, thank you for the compliment. And first of all, let me say that ice ages are not pleasant things. The last ice age ended about 10,000 years ago. And before that, in the middle of the ice age, we humans had no civilization to speak of. We were savages wandering around, desperately searching for shelter, for warmth, desperately looking for every scrap of food that we could. Most of North America was covered by a half a mile of ice. Let me repeat that. Most of North America was covered with half a mile of ice. So civilization as we know it was impossible. We lived in small bands of maybe 100 people. If the group got too big, the group would fission in half, and two tribes would separate, and then later they would war with each other. It was not a very pleasant form of existence, freezing to death, starving to death in the middle of an ice age. But then something magical happened 10,000 years ago. The ice melted. Why? We don't know. We're clueless. The leading theory is that there's a slight wobbling of the orbit of the Earth. The axis of the Earth seems to wobble a tiny bit, and averaged over thousands of years, it could cause the temperature of the Earth to rise or to fall. So we are in an interglacial period. In another 10,000 years, we'll probably have another ice age. So in other words, in 10,000 years, once again, we're going to be covered with half a mile of ice. And civilization as we know it will have to go underground or into outer space. Now, you mentioned Type 1, Type 2, Type 3 civilizations, so let me very quickly summarize that. A Type 1 civilization is maybe 100 years more advanced than us, and they control the weather. They would be able to modify the weather to avoid ice ages because it doesn't take much. It doesn't take much over thousands of years to begin to alter the temperature of the Earth, but we don't know how to do that. A Type 1 civilization is planetary. They control the weather. They can influence earthquakes and volcanoes. They have cities on the ocean. Anything planetary they control, like Buck Rogers or Flash Gordon. Type 2 is stellar. They control the power of the sun. They could avoid ice ages because they control the power of sunlight. They control stars. They have colonized the sector of the galaxy that we live in, like the Federation of Planets in Star Trek. Type 3 is galactic, like Star Wars. They control the power of black holes. They roam the galactic space lanes. But we are Type 0. We're about 100 years from being Type 1. So in other words, can we avoid an ice age? Well, first of all, the next ice age is maybe 10, 20,000 years from now. But the answer is right now, no. But in 100 years' time, we may have the technology to influence the weather itself. However, as you know, the weather is warming up. And the question is it a race against time? Will the Earth warm up to the point where life becomes unlivable? Or will we be able to harness the power of a Type 1 civilization and control the weather itself? That is a big question mark. Okay, let's move on to the next listener phone call.
Hello, my name is Hunter Gaudio from Villanova University. I saw your tweet, and I was wondering if you think that human beings can extend their average lifespan past 100 years without significant genetic modification. Thank you.
Well, I think you said the key phrase, significant genetic modification. I think that it does require genetic modification. I don't think any diet or any simple fix will allow us to lengthen our lifespan. But we'll talk about after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Well, a caller called in and said, is it possible to lengthen our lifespan? Well, the answer is yes. But can we do it without genetic modification? And that's real tough. First of all, with caloric restriction, you don't need genetic modification. You can almost double the lifespan of most animals. You eat 30% less, you live 30% longer. It's an amazing development. We've tested it out on almost all organisms, starting with yeast cells, spiders, insects, mammals, now with primates. And yeah, you eat 30% less calories, you live 30% longer. But one major species has been omitted, Homo sapiens. We complain too much. We bellyache too much. We sue the doctor if we're inconvenienced. So as a consequence, doctors don't want to do this experiment on humans. It's too difficult. Now, with genetic modification, a whole new avenue opens up. First of all, we have telomerase, an enzyme which stops the clock. Your skin cells age. They divide about 60 times, and then they go into senescence and eventually die. In fact, that's one reason why you die. There's a clock, a biological clock. Well, telomerase stops the clock. Now, what's the catch? The catch is that cancer cells also use telomerase because cancer cells are immortal. Why do cancer cells kill you? They kill you precisely because they are immortal. They grow and they grow until they form a tumor. That tumor grows and grows until it kills you. So, if we have telomerase, we could actually stop the clock. But we have to do it in a way so that cells don't become cancerous. And also, we're beginning to locate the genes involved in the aging process. If I have a car, aging takes place in the engine. Everybody knows that. But what is the engine of a cell? The engine of a cell is the mitochondria, and sure enough, that's where a lot of aging takes place. If we have genetic engineering, we can then correct the defects that accumulate in cells. So there are many ways in which aging may be reversed. The simplest way would be, for example, to scan the genes of millions of old people, then scan the genes of millions of young people, and look where aging takes place in the genome, and then fix it. Why can't we do it? A, because we haven't isolated all the genes where damage takes place, and B, even if we could, we don't have gene therapy at the level where we could at will correct misspellings in our genes. So to conclude, A, we do not have the fountain of youth, but B, is it possible? And the answer is yes. There's no reason why we can't live hundreds and hundreds of years. For example, the Greenland shark can live over 400 years of age. We know that because the eyeball of the Greenland shark adds a layer every year like a tree ring. By counting the rings, you can actually tell the age of a Greenland shark, and they are over 400 years of age. So is it possible that we could have the fountain of youth? And that is yes. Do we have it? No. But who knows? I think in the coming decades, we may get a handle on it. And yeah, I think that in the coming decades, we may be able to slow down and maybe stop the aging process. Okay, let's move on now to the next listener phone call.
Hi, my name is Steve Tensmeyer. I'm calling from Irvine, California, and I have a question. If gravity is simply mass displacing or bending four-dimensional space, then why is gravity described as a force and not simply the shape of four-dimensional space? In other words, why do we say gravity is acting on us when it really should be we're simply following the shortest path between 2 points in four-dimensional space? Or are those simply two ways of describing the same thing? Thank you.
Well, you ask a very interesting question. First of all, we have the old thinking going back to Isaac Newton of 300 years ago, thinking that gravity is a force. No, you're right. Gravity is not a force. The idea of gravity being a force was introduced by Newton because he didn't know what was causing objects to move. Objects move because they're pushed. Objects move because they're pushed by, we think, a force of some sort. But what is pushing an object as it falls under gravity? Nothing. There's nothing there pushing it. So Einstein said, no, there is something there pushing a ball as it goes to the floor. What is pushing the ball is space itself, the warping of space itself. So, for example, think of a quote from Shakespeare. Shakespeare said that we're all actors on the stage of life. That's a Newtonian picture, that we dance on the stage of life. Einstein comes along and says, no, the stage of life is warped. So as you walk across the stage of life, you think there's a force. There's no force at all. There's no force at all. But you think there's a force pushing you to the left, pushing you to the right. It is the warping of the stage itself. So in other words, to summarize all this discussion, gravity is not attracting you to the floor. Space is pushing you down into the floor. And so that, in some sense, is the essence of Einstein's great insight into gravity. Gravity is not a force at all. There's no force of attraction holding you down to the floor. It's that space on top of you is pushing you down. That's why you're sitting in your chair. That's why you're standing in your room. Not because of a pull, but because of a push. Unfortunately, we have run out of time in Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profiled some of the most amazing developments in science and technology that touch our lives. And in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, let's move right on to the next listener phone call.
Hello, Dr. Kaku. This is Anthony from San Diego. I stream your show. The infinite series, whose terms are the natural numbers 1 plus 2 plus 3 plus 4 and so on, is a very interesting and unexpected result. While that's surprising in itself, I was even more surprised to hear that it is used in practical areas such as physics and string theory. Can you describe its real-life applications and how it pertains to string theory? Thank you.
Well, yes, the natural numbers 1, 2, 3, 4 by themselves are rather interesting, but not very useful. However, we now realize that with the natural numbers, you could begin to describe the universe itself. This was first done 2,000 years ago by the Pythagoreans. In Greece, we have this school of philosophers that looked at the lyre string, and they realized that you can make harmonics on a lyre string and describe them by using the mathematics of 1, 2, 3, 4, 5. For example, when you learn music for the first time, you learn that music is based on octaves. A, B, C, D, E, F, G. We all know do, re, mi, fa, sol, la, ti, do. But why 8? Why 8? Because if I take a lyre string and I start to work out the resonances you can make on lyre strings, you can then begin to categorize all the notes that are possible. And it turns out that after 8 notes, it repeats itself. And so using integers, 1, 2, 3, 4, 5, you can then begin to count the notes that make up the basis of music. Now, why is that interesting? Because the Pythagoreans thought that you could describe reality itself, all the chemicals of the universe, using strings. Well, that failed because, well, you need a missing step. That missing step is the atom. It turns out that when you break something up, you have small particles called atoms. When you break them up, you get subatomic particles. When you break them up, you get quarks. But then the question is, what happens inside a quark? We now realize that perhaps all these subatomic particles can be described by 1, 2, 3, 4, 5. That is the notes on a vibrating string. This string is actually a rubber band. It is extremely tiny, 10 to the minus 33 centimeters across. And when you twang it, it creates all the musical notes found in music. A, B, B flat, C sharp, and so on and so forth. So all the notes that we see in music have a one-to-one relationship with subatomic particles. So then physics is the laws of harmonies of these strings. Chemistry are the melodies you can play on these strings. The universe is a symphony of these strings, all counted by the natural numbers. And the mind of God that Albert Einstein wrote about from 1925 to 1955, the mind of God is cosmic music resonating through hyperspace. So in other words, the natural numbers allow us to count the notes on a string, and these notes in turn give us the melodies which make up all the chemistry which make up the known universe. I should point out that we have not proven that string theory is the final theory, but you can go to any physics library, any physics department on the planet Earth, and yes, they either have somebody working on string theory or somebody desperately trying to learn string theory. Okay, let's move on to the next listener phone call.
Hi, this is Daniel Case, calling from Tulsa, Oklahoma. Not any particular radio station, but my question is, string theory asserts that there are at least 11 dimensions, which is 7 more than humans can perceive. And my question is, if the theory of the multiverse is true, and if humanity develops the tools or instrumentation required to physically observe or measure these 7 new dimensions, could these dimensions offer glimpses or correlation into other universes, or would every dimension we find be constricted to our observable universe? Thank you.
Well, you ask a question that's at the cutting edge of string theory itself, but let's try to break it down into the various pieces. First of all, we believe in a universe, that is one world. That's where the word uni comes in, one world. However, string theory takes us one step farther. It takes us to a multiverse of possible parallel universes. Now, I should point out that this has not been proven. It is a theory. It's a theory accepted by, I think, a vast majority of theoretical physicists who work in the field, but that doesn't mean it's correct. So Einstein gives us a picture of the universe being a bubble. The bubble is expanding. The string theory now gives us the idea that there could be other bubbles out there, giving us a bubble bath of universes. And when these bubbles collide, that gives us a Big Bang. So Big Bangs are happening all the time. These bubbles are splitting apart, they're reforming, and each time it collides or reforms, that's called a Big Bang. Now, for me, this was interesting. Well, let's take a short commercial break, and we'll talk about how this has theological implications and even religious implications as well. Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. Well, before the break, we had a very interesting call about string theory. You see, string theory has a weak spot. If you were to criticize string theory, you would say that, well, string theory believes not just in 3 dimensions, but 11 dimensions. And you might say to yourself, what? That sounds like Star Trek. That sounds like science fiction, a multiverse of parallel universes. Come on, give me a break. This is science fiction. Well, yeah, it is science fiction, but it's also based on the latest theory coming out of theoretical physics. The quantum theory said that if there was a Big Bang, it could happen again, and again, and again. There could be multiple bangs happening all the time, says, according to the principles of the quantum theory, meaning that universes could be being created even as we speak, giving rise to a multiverse of universes. Now, the questioner asked about 11 dimensions. First of all, why can't we see them, and where are they? Well, we think that our universe is 3 dimensions, has 3 dimensions like length, width, and height. So these other dimensions must have curled up, that they're there, but they're simply too small to be seen. I like to think of it as what I believe was true when I was a little boy growing up outside of San Francisco. I used to visit the Japanese tea garden years ago and look at the carp swimming just beneath the surface of a shallow pond. And then I asked myself a question that only a child would ask, and that is, what would it be like to be a fish? And I realized what a strange world the world of fishes must live in. Their world is two-dimensional. They can swim forward, backward, left, right, but that's it. That's all they could swim. And their eyes only go left, right. And so in other words, their world is a two-dimensional world. If somebody were to say that there's a world of up, the third dimension, the world beyond the pond, then people would say, that's crazy. That's nonsense. The pond is everything. And then I imagined there was a scientist fish, who lived in the pond, and the scientist fish would say, bah, humbug, ha, there's no such thing as hyperspace, third dimension, the world of up. The pond is everything. Everything you can see is the pond, and the pond is in two dimensions. And then, as a child, I imagined reaching down and grabbing one of the fish, lifting the fish into the world of up, into the world of the third dimension. What would the fish see? He would see beings breathing without water, a new law of biology. Beings moving without fins, a new law of physics. A new world in the world of up. And then I put the fish back down, and then what would he tell his fellow fish? He would say, oh my God, there is a world beyond the pond, a world that we cannot see very well. We can only see slices of the world. But as I drifted in the world of up, my eyes could see slices of this strange world of the third dimension. Well, today we physicists believe, not all of us, but many physicists believe, that we are the fish. We spend all our lives in three dimensions, moving left, right, up, down, forward, backward. Our eyes can only see in three dimensions, and we laugh and snicker anytime someone talks about universes beyond what we can see and hear. Well, we scientists are not laughing anymore. We now realize that string theory is the only theory known to science that can unify the fundamental forces of the world into one comprehensive theory. That was the dream of Albert Einstein, to create a theory of everything. And the only other theory that works is string theory. Now, some people come up to me and say, Professor, maybe I don't like string theory. Give me an alternative. Give me plan B. Give me another theory of everything. And the answer is quite simple. There is none. I repeat, this is the only game in town. If you are a physicist and you want to work on the unified field theory, unifying gravity with the quantum forces, this is the only theory which does it. No other theory can make the claim. And so, well, maybe it's wrong. After all, physics deals with things that are measurable. We cannot yet measure the higher octaves of the string. So some people say, well, how do we go about proving that this is the final theory? Well, that's difficult because to experimentally verify it, you would have to find the next notes of the string that are predicted by string theory, and we think that's dark matter. We think that dark matter, this strange, mysterious, invisible matter that surrounds the galaxy, is nothing but the next octave of a vibrating string. But the cynic can simply say, well, is that proof? Is that enough? Well, I'm a theoretical physicist. I work with mathematics, pure mathematics, and I think that one day some enterprising physicist will completely solve the theory and show that this theory fits all the data. At that point, it would be obvious that this really is the theory of everything. And so once again, to summarize, the question is, where are these strings? Why can't we see them? Where are these higher dimensions? These higher dimensions have curled up to the point that you cannot see them anymore. For example, if I take a sheet of paper that's two-dimensional, but I roll it up into a straw, the straw is one-dimensional. It only has a dimension of length. If I unravel it, it has two dimensions. But of course, it's nothing but a sheet of paper. So a wrapped up sheet of paper loses one dimension. So we think that in the beginning of time, there were 11 dimensions, and 7 of them curled up. Why? Well, that's what I'm working on right now. That's one of the questions that I'm working with, is to try to figure out why 7 of these dimensions curled up, and that's the reason why we live in a 3-dimensional world of today. 1 dimension of time and 10 dimensions of space. And if you want to know more about this, well, get a copy of my book, Hyperspace, which was, in fact, the first popular book that introduced the public to string theory. Okay, let's move right along now to the next listener phone call.
Hi, Dr. Kaku. My name is Alonzo, calling from New York City. Wouldn't a time machine also have to be a spacecraft with the ability to move to any point in space along with the specified time? And because of that, wouldn't the traveler have to know the space-time coordinates of everything that was in the past and that will ever be in the future? Thank you.
Well, you ask a very important question that we physicists are actually studying right now because, of course, first of all, we don't have time machines. But one day, perhaps we will. And then the question is, if we go backwards in time, what about space? Do you go back to the exact same spot except in a different time period? Or for that matter, the Earth spins around the sun. The Earth moves. And therefore, if you go backwards in time, do you wind up where the Earth used to be? In which case, you would suffocate in the vacuum of space and time. So this is a valid question. In the movie Back to the Future, for example, Michael J. Fox jumps into his DeLorean, and he winds up at exactly the same spot on the Earth, except shifted in time. But you may say to yourself, now wait a minute. The Earth spins. The Earth goes around the sun. In fact, right now, you are moving at about 1,000 miles per hour. Now, that sounds crazy, but it's true. You're moving at least 1,000 miles per hour because you're moving around the center of the Earth. The Earth is 24,000 miles in circumference, and you circumvent the Earth every 24 hours at 1,000 miles per hour. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question about time machines, and yes, we physicists do study time machines. It's often stated, however, that Einstein's theory does not allow for time travel. That's actually not true. Einstein's first theory of 1905 does not allow for time travel, and many people study special relativity but never go to the next theory. The next theory is called general relativity, a theory of space-time and gravity, and that does allow for time travel. Einstein himself was worried about this. Einstein thought that time travel could pose a problem for his theory because of the fact that time travel seems to violate common sense. If you could go backwards in time and meet yourself as a child, you could even kill yourself as a child, commit suicide in the past. But if you commit suicide in the past, then how could you be alive today if you just shot yourself in the past? This is a paradox. And we physicists study these things. I have friends of mine who actually publish papers on time travel. Now, the questioner that called in asked about the fact that if you go backwards in time, don't you also have to specify the place? Or don't you wind up in outer space where the Earth used to be, but is not there anymore in the future? And the answer is yes. One day, when we do build a time machine, if and when, we'll have to specify the coordinates of space as well as time. Otherwise, you could wind up in the middle of a vacuum where the Earth used to be centuries ago, for example. So that's something that you have to put into consideration. Now, there are several designs for time machines. The simplest one was devised in 1949 by a mathematician, Kurt Gödel. If the universe rotated and you go around the universe and make one complete circuit, then you can go backwards in time. Now, Einstein was very worried about this solution. In fact, wrote about his problems with this solution of his own equations. But Einstein concluded that, don't worry, the universe does not rotate, it expands, and therefore we don't have to worry about time travel. Well, yeah, the universe expands, it doesn't rotate. If it did rotate, then perhaps time travel would be commonplace. But since then, since 1949, many solutions of Einstein's equations have been discovered, which do allow for certain forms of time travel. What's the catch? There's always a catch, right? And that is you have to have a very stringent set of conditions to make these time machines possible. First of all, you have to have energy comparable to a black hole to create a hole in space. That is very difficult, of course, to play with a black hole. Second, you have to have negative matter or negative energy to stabilize it so you don't get crushed, so it doesn't blow up. To stabilize it, you need an exotic form of matter energy, negative energy and negative matter. And we've never seen negative matter before. It would fall up rather than falling down. So the conclusion is that, yes, time travel is allowed by Einstein's equations, but whether or not it is physically possible to build such a machine requires a technology far more advanced than anything found on our planet Earth. So don't expect an amateur inventor to create a time machine in his or her garage. It's not going to happen. The energy required is that of a black hole. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're throwing the lines open. Open mic. It is open mic on Science Fantastic. Well, before the break, we had a quick question about time travel. Yes, we physicists believe that time travel is a possibility. It is allowed by Einstein's equations, but the energy necessary to warp space and time in that fashion is humongous. We're talking about the energy of a black hole. And we at the present time cannot control that cosmic energy necessary to open up a gateway through space and time. And then the paradox. What happens if you go backwards in time and meet yourself as a child and you kill yourself? Can you commit suicide in the past? Well, how do we resolve that? We resolve that by the quantum theory. We think that when you go backwards in time, the timeline splits, forks into two roads, and one timeline gives us our past, the other timeline gives us an alternate reality. And so quantum mechanics gives us a solution to all the time travel paradoxes. So if you go backwards in time and save Abraham Lincoln from being assassinated at the Ford Theater, you save somebody else's Abraham Lincoln. Your Abraham Lincoln died at the Ford Theater at the close of the Civil War. Okay, let's move on now to the next listener phone call.
My name is Connor Crow. I'm calling from Baltimore, Maryland. And my question is there any particular reason we only have one time dimension? And how might our universe be messier or less disorganized if we had two? Thank you.
Wow. Well, believe it or not, you ask a question that some of my physicist friends at Harvard have also asked. Is it possible to have a double-time universe? Well, what would a double-time universe look like? Well, I once saw a movie by David Niven where he was a pilot during the war, and he was shot down and died. But the angels who came down to pick him up realized, uh-oh, we made a mistake. A clerical mistake. He was not supposed to die. And so he was sent to heaven where they had to analyze the whole question of, well, did we really make a mistake? Did he die prematurely when he was not supposed to die? And there was one scene where David Niven goes back to the planet Earth and time stops. He wanders around the Earth. Everyone is motionless. He is moving in a double-time universe. Everybody else moves in normal time. But he's moving in a different time. And that's what a double-time universe would look like. In a double-time universe, you can move perpendicular to time so that everything you see around you is stopped. But you can move. And, of course, if you could do that, you could become a super criminal. You could do all sorts of mischief, rob banks and things like that. Everyone is stationary and doesn't know what to do, is not even aware of your presence. So a double-time universe would be very strange if we lived in one. Now, believe it or not, there's some physicists who work in double-time universes. You see, string theory does more than simply predict our universe that we see around us. It also predicts other universes that may not exist. Because, of course, an equation, like an equation for light, has many solutions. Light bulbs, television sets, laser beams, they're all solutions of an equation for light. So if you have an equation for the universe, then there should be alternate solutions with alternate times. And so, yes, there is a version of string theory called F theory with 2 dimensions of time. Wow! Think about that. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a quick question about, is it possible to have a double-time universe, a universe with more than 1 dimension of time? And the answer is, well, yeah, there are physicists who work in this. They're at Harvard University. The theory is called F theory, F meaning the father of strings. And they think that perhaps string theory itself comes from a 12-dimensional universe. 10 dimensions of space-time, 10 dimensions of space, and 2 dimensions of time. Google it, and you'll find references to how some physicists believe that a double-time universe may be possible. Then the question is, what about 13, 14, 15? Does it end at that point? And the answer is yes. It turns out that universes become self-contradictory in dimensions like 13, 14. So there's a reason why we think that string theory selects out 11 and 10 and 12 dimensions. These dimensions, 10, 11, 12 dimensions, give you stable universes, universes where we have protons and quarks. In these other universes, we have anomalies. They're unstable, and for the most part, we think they decay down to 10, 11, and 12 dimensional universes. Wow! That comes from the world of pure mathematics, the world that I live in. Okay, let's move on now to the next listener phone call.
Yes, this is Gary from Dallas, and I had a question on how do galaxies form, and do stars form first and then aggregate into a galaxy, or does the galaxy come first, or do they kind of evolve both together? Thank you very much.
Well, you ask a question that, believe it or not, astronomers debate even today. Which came first, the chicken or the egg? But let's sort of define terms ahead of time. Stars, of course, are these points of light that you see in the night sky. But they aggregate, and they form galaxies. Galaxies are huge. Galaxies like our Milky Way contain 100 billion stars. 100 billion stars. And how big is it? About 100,000 light years across. They are gigantic. And then how old are they? Well, our Milky Way galaxy is perhaps 10 billion years old. How old is the universe? Perhaps around 13 billion years old. And so then the question is, what came first after the Big Bang? Well, the short answer is we don't know. But when we go backwards in time with our telescopes, with the Hubble Space Telescopes, we can see that about 1 billion years after the Big Bang, about 1 billion years after the Big Bang, that's when the first galaxies and the first stars began to condense. That's the oldest evidence we see. Beyond that, beyond 12 billion years, we just see darkness. Because, of course, back then, atoms did not condense yet. There was no atoms out of which we could create stars and galaxies. And so which came first, the chicken or the egg? The best answer is they probably came at the same time. That out of the Big Bang, we had a super hot gas, so hot the atoms could not form. Once atoms formed, they would be ripped apart by random collisions. And so for about 1 billion years, there was darkness. darkness throughout the universe. And then after that, things could cool down to the point where we would have stable stars, stable atoms, and out of the atoms came hydrogen. Hydrogen began to congregate into stars and eventually galaxies. And so the answer to the question, which came first, the galaxy or the star? Well, the short answer is we don't know, but we think that about 1 billion years after creation, that's when you get the first condensation of atoms to create stars and galaxies. And we think they probably were created simultaneously at the same time. Now, here is a cutting-edge question. At the center of galaxies is a black hole. Almost every galaxy we find in space has a black hole at the center. So which came first, the black hole or the galaxy? And believe it or not, this is a raging topic in astronomical circles. We don't know the answer. The oldest galaxies are quasars, quasi-stellar objects. These are the oldest galaxies we can see that go back right after the Big Bang. And what are quasars? We think that quasars are raging black holes where the galaxy is not quite formed yet. And so we have yet another question. Which came first, the black hole or the Milky Way galaxy? All we can say is that out of the Big Bang came some stars, galaxies, and quasars, quasars being raging black holes, and maybe, just maybe, our galaxy is a remnant of an ancient quasar. And so it means that maybe our own galaxy once upon a time had that humongous black hole that gradually cooled down to become the rather quiet black hole at the center of the Milky Way galaxy. Okay, well, let's move on to the next listener phone call.
Don Tiffon, Twitter. And my question is, what physical phenomena is the single, fundamental, and necessary cause of all other phenomena?
Well, we think that all physical phenomena originally came out of the Big Bang. First of all, we have 4 major types of phenomena. First of all, we have gravitational phenomena that gives us stars. We have electromagnetic phenomena that gives us atoms. We have nuclear phenomena that gives us the nucleus of the atoms and the energy source of the stars. So we think that 4 fundamental phenomena govern everything we see around us, 4 forces. But then the question is, where did the 4 forces come from? They came from the Big Bang. So think of the Big Bang as a gigantic crystal that shattered at the beginning of time, leaving us fragments. These fragments are the 4 fundamental forces. And then the next question is, where did the Big Bang come from? Well, at that point, we don't know the answer, but we think it came from string theory. That string theory shows that you can have instabilities in space and time, and these instabilities give us the Big Bang. Okay, well, unfortunately, that's it for Science Fantastics.